Hi everyone, I'm Xiangyi, and in this video we will go through my FYP project, Non-Stationary Fuzzy Transformer with applications in reinforcement-based portfolio rebalancing. I want to take this opportunity to express my gratitude to my FYP supervisor, Prof. Kwek Kyok Chai, for his tireless and invaluable guidance. In this project, we propose a neural fuzzy system known as non-stationary fuzzy transformer to validate the effectiveness of transformer as a time series forecasting methodology. We introduce semantic interpretations to the deep learning network through the embedding of a parallel fuzzy network. The hope is for the forecasted prices by NSFT to enhance trend reversal signals and produce accurate entry and exit strategies for investors. To validate the performance of the signals, we train two different reinforcement learning agents, one to account for the lag in the generated signals and another to dynamically reallocate positions in the portfolio. To understand what this project is really about, let's cover some big ideas that motivate the project. Firstly, the prediction of the price movement of a single stock is largely inaccurate due to the inherent randomness of the price, which can be caused by unpredictable variables such as changes in supply and demand or the occurrence of certain catastrophes. However, when we formulate broad sector indices, there exist more stable and predictable patterns due to the diversification inherent in these indices, as the movement of individual stocks within the sector can balance each other out. Finally, while data-driven deep learning models are effective, they are often not interpretable, which is crucial in industries where each decision incurs high costs, such as healthcare or finance. We first explore the potential sectoral indices. According to Spider Research, sectors perform differently during different phases of a business cycle. For instance, during expansion, financials and technology sectors excel, while in a recovery, real estate and consumer discretionary perform better. However, the research also revealed that there exist anomalies where commodities-related sectors, such as materials and energy, did not make it to any top sectors or bottom sectors across all cycle phases, indicating that the energy sector may not be as sensitive to the US economic cycle as expected. This is due to the fungibility of energy on the global market, where profits are driven more by international supply and demand than the US market. For the purpose of our project, we select energy, real estate, and technology firms to build our index upon. Before we begin the construction of the non-stationary fuzzy transformer, we need to identify the purpose of the predictions. Unfortunately, even if we are better able to predict prices, these prices are still too inaccurate to be traded on. Instead, we look at the potential of predicted prices. Firstly, we introduce the concept of trend reversal indicators. These are trading strategies formulated within the industry over the last few decades. These indicators assist investors in trades by identifying the turning points of the market. Some examples of the indicators include simple moving average, relative strength index, and moving average convergence divergence. However, most of these strategies incorporate some form of moving averages, resulting in most of the indicators to perform poorly as they lag. We explore one example of that in the following slide. The SMA is formulated by creating two lines, the slow blue line, which is the rolling average of 200 days, and the fast black line, which is the rolling average of 50 days. The crossing over of the slow line above the fast line corresponds to the sell signal and vice versa for the buy signal. However, since aggregation is done with the n look-back days, the moving average created should mathematically be centered around n over 2 days ago, which corresponds to a lag. As you can see, the trough occurs at this point, but the SMA only produces a sell signal a few days later. Clearly, these signals are not very helpful because they lag. However, this lag can be quickly resolved if incorporated look-ahead values, which we will refer to as hindsight. We evaluate the performance of the strategy generated by the hindsight indicators across different indicators, as illustrated by the orange line. We show only a few examples for the sake of the presentation. After systematic trials and errors on my end, we discovered that clearly not all indicators perform well with hindsight values incorporated, with the exception of moving average convergence divergence. MACD also operates by defining two lines, the MACD line and the signal line. When the MACD line crosses the signal line, a bullish signal is generated and vice versa. Here, we identify the purpose of the forecasted prices, which is to better approximate the future trends to obtain a better trading indicator. In the following section, we cover the architecture of our non-stationary fuzzy transformer for price predictions. Conventionally, RNN architectures like LSTM has proven superior for long-term forecasting. However, in the spirit of exploration, we turn to transformers, which has been revolutionizing the domains of NLP in recent years. Transformers operate on an encoder-decoder structure with attention mechanism incorporated. Encoders help to learn embeddings in the input sequence while decoders generate a new sequence. However, due to the non-sequential nature of the model requires additional positional embedding information to be supplied. The non-sequential nature also means transformers are parallelizable and has infinite recall. However, transformers have not been very successful for time series forecasting due to its inability to capture concept drift, where statistical properties of the target variable in a predictive modeling task change over time. Furthermore, position embeddings are only a static way of representing positions and may not be enough for sequential prediction of time series data. Instead, we turn to variants of non-stationary transformers which have been conceptualized by other researchers. One of them is the non-stationary transformers, which is the state-of-the-art transformer for short-term time series forecasting. This variant tackles the problem of concept drift, also known as non-stationarity in their paper, through the formulation of two components: series stationarization and destationary attention. Series stationarization attenuates non-stationarity in the input time series by normalizing the temporal dimension using a sliding window and unifies the statistics of each input series, making the distribution more stable. The destationary attention is introduced to reincorporate the temporal dependencies that would have been otherwise normalized by series stationarization. As we can see here, series stationarization is adopted as a wrapper to the original transformer model to normalize the incoming series and denormalize the output, while the destationary attention replaces the original attention mechanism by scaling the temporal dependency weights using destationary factors. To visualize what destationarized attention is, we see from part B in the figure that series stationarization can generate the same stationarized input from distinct time series, resulting in identical attention which fails to capture crucial temporal dependencies. The destationary attention mechanism approximates the attention from the original series and reincorporates it back into the model. For the exact math, please refer to the original paper for non-stationary transformer. As the next step, we build a parallel fuzzy network for the creation of a fuzzy rule-base. By fuzzifying the inputs and outputs and training them on the neural network model, we aim to integrate the fuzzy network with non-stationary transformer to create a neural fuzzy network. During post-processing, the fuzzy mechanism serves as a tagging mechanism to generate the rule base in the fuzzy system. They do not backpropagate errors, unlike neural networks, but instead use decay factor and retention factor to calculate the weight of the activations over repeated activations. In this diagram, we showcase the embedding of the fuzzy network in parallel to the non-stationary transformer. The fuzzified inputs and outputs serve as a vocabulary for the antecedent and consequent in fuzzy logic, and the resulting weights for each activation path is tagged during post-processing to form the rule base. Next, we build the indices required for training. As previously mentioned, energy, real estate, and technology have been chosen as the three sectors. We begin with a univariate time series data of close prices. These are subsequently feature engineered into price, delta, and momentum that has been locally normalized in a sliding window against the last 20 time steps, and delta and momentum normalized against price. The motivation for the feature engineering is to generate features that mitigate concept drift. These features will subsequently be fuzzified through membership projections onto clusters, using the state-of-the-art K-medoids clustering technique, bandit PEM, and trained using our non-stationary fuzzy transformer. Finally, we obtain the forecast results and perform a goodness of fit analysis against the actual price. We observe that, as expected, the accuracy of the price predictions decay with the time extending into the future. Interestingly, energy has a lower R-squared score than the other sectors across all time steps, which may be a result of energy firm's susceptibility to more unpredictable variables, such as both natural and man-made catastrophes. Here, we see that at time steps further into the future, the predicted price appears to be lagging. While in this slide, we compare the same time step T1 of real estate against energy and see that prices predicted for energy appears to be more erratic. Next, we incorporate the predicted 5-day look-ahead result into the MACD indicator that we previously identified and trade on the signals that are generated by the new predicted indicator using a long-only strategy. Unfortunately, as demonstrated by the green line, the returns are subpar. To understand why, we visually plot the predicted MACD and signal lines against the perfect hindsight lines and perform a goodness of fit analysis on them. Clearly, from the analysis, it appears that the R-square score for the predicted lines are much closer to the hindsight lines than the vanilla lines, where no future values are incorporated. So why is the performance so poor? We observe here that when we separate the two sets of lines, the predicted lines are actually much noisier than the hindsight lines. Furthermore, when we analyze the signals generated by the two signals, we observe that not only are there many buy and sell signals generated for the predicted indicator, they also tend to lag by a couple of days. So we have identified the problems. The signals are basically noisy and late. To validate the hypothesis that the signals are still lagging, we shift the predicted signal by just 1 day forward and trade using the same long-only strategy. Astoundingly, we observe that the generated signals are way higher than all the other benchmarks. To resolve this issue of lag, we hypothesize a lag accounting reinforcement learning agent that's able to anticipate the crossover of MACD and signal lines and trade before the actual crossing. For the purpose of this project, we implement an RL agent using proximal policy optimization by stable baseline tree. PPO is able to balance trade-off between exploration and exploitation by clipping the objective function such that the agent is able to take the largest step to improve policy without causing destructive updates. In this slide, we identify the states, action, and rewards for the agent. The states are the predicted MACD and signal lines, their signals, the close price, and the current position. The agent can buy, hold, or sell, and if the agent makes a correct trade 1 day before anticipated crossover, they are rewarded, else they are penalized. Furthermore, the agent has to make trades that optimize long-term balance. It is important to note here that the rewards are selected based on manual trial and error as opposed to rigorous optimization techniques. As you can see in this diagram, the IR agent that has been tuned to anticipate crossover actually makes very similar trades to the strategy produced by the hindsight indicator and is able to attain substantial returns, as demonstrated by the purple line. In this table, we showcase the returns of the lag accounting RL agent against the other strategies. We observe that with the exception of real estate index, the RL agent is able to achieve substantial improvement over the vanilla indicator. As the next step, we want to diversify our portfolio and not trade on a single index, where bets have to be made and may result in substantial losses, as observed by the real estate anomaly in the previous slide. To do so, we define a portfolio rebalancing RL agent with the following states, actions, and rewards. The goal is to incentivize the agent to increase cumulative balance in the portfolio. Similarly, the decisions of the agents are simulated using a long-only strategy, and we can see that the rebalancing agent performs much better than buying and holding any of the individual indices. We see from the results that the portfolio rebalancing agent is able to generate 149% return on a $10,000 principal, yielding the highest return across all strategies with a decently small max drawdown. In this slide, we present the positions and the proportions of the portfolios as executed by the rebalancing agent. To briefly conclude, in this project, we endeavor on the creation of a non-stationary fuzzy transformers, validate the utility of forecasts by incorporating them into MACD to generate more punctual signal, and train 2 RL agents to identify the best strategy to trade on a single index and manage a portfolio. Due to the constraint of time, the project has not been sufficiently explored. For future work, we can consider benchmarking the transformer's performance against other temporal neural networks, such as RNN and LSTM, and also further improve on the optimization of the RL agent. Lastly, other feature engineering techniques such as path signatures should be explored, which could aid in the predictability of the NSFT. Thank you.